discussion of one-step methods. Last time I showed you the simplest one-step method for solving initial value problem, as Euler's method. Um, so with Euler's method, the error is, as was proven last time, is order h. H just h of first power, where h, this is the notation we'll be using all chapter long, is the time step size. So convergence is slow. Can we obtain higher order accurate methods? Where p is greater than 1. Now there's one approach that can be used to obtain higher order methods. So can use more terms in a Taylor expansion. So Euler's method used only the first two terms in the Taylor expansion, so we could go ahead and use more terms. But the difficulty with that is we have to approximate. Okay, so after just a little bit of recording, it got a QuickTime crashed. So let's try this again. So to get higher order terms, we can just try matching more terms in a Taylor expansion of the exact solution, but for the general initial value problem, which I'll repeat for ty. Okay. So we have to approximate higher order derivatives, or just derivatives in general. That approach is going to be used in a little bit when I'll show how to derive a second order method. But before we get into that illustration of order of accuracy and how to solve initial value problems in MATLAB. So several ODE solvers using mostly high order methods of the kind that we're going to see throughout this chapter. I'm going to do a demonstration in MATLAB. Okay, so first I'll get a diary going. Okay. Whoops. I didn't want to name it that. Okay. Okay. So I can solve a very simple initial value problem. Y prime is equal to y. Y0 is equal to 1. So the exact solution would just be y of t equals e to the t. I will time stepping. I'll be using time stepping. I need to set a final time. So referred to as capital T in the last class. All right, so I'll just use t equals 1. Okay, so one of these ODE solvers. I'll use ODE 2.3. So this uses a combination of second and third order methods. Really, it's an adaptive time stepping method. And there's 3 parameters in the simplest usage. So the first one is a function handle for the function f of ty. So I'll just define a function. F of ty is equal to y. So that's what this does. It's an anonymous function. It takes arguments t and y, and then the y value is the output. And then the next the next argument is an interval in time, where you give the initial time and the final time. So I'm going to time step from 0 to 1. And then I'll specify the initial value, which would just be 1. Okay, so f of ty, t0 and capital T, so I'll call it tf, so initial time and final time. and then y0. So those are the arguments to this function for the simplest usage. So I'll go ahead and solve it. Should put a semicolon there. So here's the output. So the first output, capital T, is a vector, a column vector of t values. And then the second output, capital Y, that's the actual solution. So the values of y of t corresponding to these t values. So it makes it easy to plot the solution y of t. I can plot, so if I do plot, make sure don't have any figure windows going. So it plots capital T, capital Y. And there it is. Then this definitely looks like e to the t. And we see the last value here. E is 2.718281828, so it matches the first 4 digits at least. So it's reasonably accurate. Now, to get the error, I want the exact solution. So yex is just, I'll just use the exponential function with these t values plugged in. So that way I have the approximate solution and the exact solution that I can examine side by side. If we put them next to each other, use the same initial value, of course, those will match. And it's fairly accurate. It's matching a few digits anyway. But I want a simple measure of error. So I'm going to do norm. So it would be square root of sum of squares of y minus yex over the norm of yex. So this is a vector 2 norm. Recall our discussion of norms for iterative methods. And so that's quite accurate. So it's 2.8 times 10 to the minus 5. Not bad. Okay, so, all right. I'm trying to think how I could use this to establish order of accuracy. Okay, because these ODE solvers use adaptive time stepping. Notice I only picked the initial time and the final time. It picked times in between. But I believe I can force it to pick times I want by giving, so 0 to 1, a vector of values from 0 to 1 of spacing of 1/10. Okay. So in that case, my t values will be from 0 to 1 of the spacing 1/10. So now I will get the exact solution of these t values and look at the error. Okay, so like before, it's 1 over 10 to the minus 5. Okay, and I'm going to call this error 10. So the error with 10 time steps between 0 and 1. Because now I'm going to solve it again. But I want to use half the spacing. So it'll be 20 time steps altogether. And then I'll substitute the exact solution at these t values. So we look at the time values. So it's 0 to 1 and spacing of 0.05, just like I wanted. And now I will compute the error again of 20 time steps. Interesting. The error was about the same. Okay. So I guess this is not the order of accuracy demonstration that I was hoping for. Okay. It's probably a byproduct of MATLAB's adaptive time stepping that it tries to reach a certain tolerance instead of just taking time steps. So sorry about that. At least I got to demonstrate how to use these ODE solvers. Normally, for order of accuracy, if I reduce h by a factor of 2, like I did here, the error should decrease by a factor of 2 to the p, where p is the order of accuracy. And this ODE solver, ODE23, uses a combination of second and third order methods. There are several ODE solvers. If I do help ODE23. Okay. Here we have several more. So ODE 4.5 uses fourth and fifth order methods. ODE 1.5s uses a variable order time stepping from first to fifth order. The S means stiff. Stiff ODEs and system ODEs are quite difficult to solve. That's something that'll cover toward the end of the chapter. So, okay. Normally I'd edit this out the video, but oh well. But this is how you solve ODEs in MATLAB. It's just not easy to use these ODE solvers to demonstrate order of accuracy because of their adaptive time stepping. And I tried to trick it, but I guess it was too smart for me. Okay, but what you would be doing for homework is writing your own time stepping methods. So functions that implement time stepping methods that I'll be showing here in class. Speaking of which, okay, let me turn off that diary. Okay, now I should mention sort of y's. Suppose I was solving a system of ODEs, so y has several components. So I'd be passing a vector for y0. What these ODE solvers will do is still the column vector of t values, and then here each row of capital Y is a value of a solution at time t, which is a vector. So if the first row would be y naught, the second row would be y to first time, the third row is y to the second time step, and so on. So if I'm solving a system of say 5 ODEs, so y naught is a vector of 5 components. So this capital Y here, the output, will have 5 columns to hold those components at each time. Okay. Now, how to obtain a high order method. Okay, so there are many high order methods, and we'll see different kinds, but here's one approach to deriving a high order method. So the Runge-Kutta methods are high order methods that use several evaluations of a function f of ty, the time derivative. And the time values used is in the interval tn to tn plus 1. So we're time stepping from time n to time n plus 1. We'll choose various t values in this interval to plug into here, and appropriate y values also. So to show how such method is derived, we impose a form on the method. Yn plus 1 is equal to yn plus ah f of tn yn. So far, if I set a equals 1, this is just Euler's method. But I'm going to add another term here. bh f of tn plus alpha yn plus beta. So I have 3 unknowns here. Actually 4 unknowns. A, B, alpha, and beta. So I need to figure out how I can choose A, B, alpha, and beta to try to get as high order of accuracy as possible. So at least we will try to get second order accuracy. Now, so really it's going to be a pattern matching exercise. So what I will do here is look at the all right. I'm going to do a Taylor expansion at time t plus h. So t plus h. So t you can think of as tn. So it's our starting time, and t plus h is our ending time for this time step. So y of t plus hf of t y of t. Because this is y prime plus next term in a Taylor expansion would be y double prime, but since y prime is equal to f, then derivative of f of t y of t, derivative of this with respect to t, that would be y double prime. And so the idea is we want to try to match at least up to this point. The next term will be h cubed over 3 times the third derivative, but we won't be needing that for this derivation. If I had more unknowns, then I would. So then I'm going to substitute the exact solution into my proposed method. Y of t plus h is equal to y of t plus ah f of t y of t plus bh f of t plus alpha y of t plus beta. All right. So if I can find a, b, alpha, and beta that make all of these agree as much as I can, then I'll have my method. Now, there are certain things that already match. So y of t plus h and y of t. So we don't need to worry about those. So I'm just going to get rid of them. Okay. The other thing is, we have a common factor of h in every term. So I will get rid of those also. Okay. All right, so I need these to line up. Now, what's more, let's see. Actually, before there isn't anything else I can get rid of, because on the one hand, I might think, oh, I could just set a equal 1. But that's actually not a good idea yet, because what if, when I work this out, I get another term, f of t, y of t? Or if I work this out. So something here could introduce an additional term, so I have to be careful about that. So what I'm going to do is, for this part, I'm going to use the chain rule to work out this derivative. So that's going to be with respect to t plus, and all of this is multiplied by h over 2, and I'm going to have partial f with respect to y. F t, y t. And then, because y t depends on t, I need to include dy dt. But dy dt is equal to f. I'm going to put it over here just so it doesn't get confused with this. Actually, I'm going to shorten the notation here. So this will be ft, and then this other derivative here will be fy. Okay. So that is now worked out to this. So now I need to see what I can do with this to try to get it to match. And for that, I use what is known as multivariable Taylor expansion applied to this part right here. So the first term is going to be the same, AFTYT plus B. So you can Taylor expand around Ty of t. So that'll be f of Ty of t. So sure enough, I have these two terms to match against this. The next term, now normally in Taylor expansion, I have the value of f, and then I have plus value of a derivative of f times the difference in arguments. But this is multivariable Taylor expansion. I have to take both partial derivatives into account. So that's going to be ft of Ty of t times the difference between this argument and t, which is just alpha. And then I will have plus df dy times the difference between this argument and y of t. But that's just going to be beta. So now, and there would be more terms here. I just won't need them. Okay. So now if I match up all of these, first of all, I can combine these two terms, the ones that involve just plain old f of ty of t. So I have a plus b. So now I don't need that anymore. Okay. So now these terms match up. And then I need to match up terms involving ft and also terms involving fy. So by matching these up, we have a plus b is equal to 1. Then if I match up the ft terms, I have, b alpha is equal to h over 2. And then I have b beta is equal to, so here I just have h over 2 fy. Here I have fy b beta. So b beta has to equal to everything in this term except for the df dy. So that's going to be h over 2 f of t y of t. All right. So, so the thing is, there's actually some flexibility here in terms of what method we could obtain by choosing A, B, alpha, and beta that satisfy all of these. So first option, I'll set A equals 0, which means B has to equal 1. Then alpha has to equal h over 2. And then beta is equal to, since b equals 1, hf over 2. And what is the resulting method? So yn plus 1 is equal to yn plus b, which is 1. So then I have hf. So I'm looking up here, tn plus alpha. So that's going to be tn plus h over 2. And then I have yn plus beta. So I have yn plus h over 2 f of tn yn. So that's what I'm filling here, tn yn. So what do we have here? This is called the, okay. Let's spill over into a new page. All right. So this method is called the midpoint method because we're evaluating f at the midpoint of the interval in time between tn and tn plus 1. And here, the second argument to f here, this is an approximation of y tn plus h over 2, the exact solution of time, by Euler's method. If you use Euler's method with a time step of h over 2, then this is Euler's method, approximating solution at the midpoint in time. So this is plugged into f, so you have this time and then the approximate solution at this same time. And now we, so it's like using a midpoint rule for integration that was covered last semester to approximate y at tn plus 1. So that's one option. Option 2, we have a and b equal to 1/2. Okay. So that would mean that, let's see. All right. I'll start to write the method. So y n plus 1 is equal to yn plus h over 2. So if I go back to the form of my method, a and b, so a and b are both equal to 1/2, so I have h over 2 here, I'll have h over 2 here. Okay, so now I have f t n y n plus, that's for the a term, and for b term I have, okay, so let's see what the arguments are. If I go back to my equations, if b is equal to 1/2 and b alpha equals h over 2, I set 1/2 here, the 2's in the denominator cancel, so alpha is just going to be equal to h. Alright, so now I'll have tn plus 1. And then, if I go to beta, b is h over 2, b is 1/2. So again, the 2's in the denominator cancel, so beta is equal to hf instead of h over 2f. So I'll fill that in down here. So yn plus hf tn yn. Okay, and so this is the explicit trapezoidal method. And once again, a second argument to f in second term, this term, is the Euler's approximation of y of t n plus 1. Okay. So, so we're approximating, so we're evaluating f at tn and tn plus 1, the endpoints of our time interval instead of a midpoint like in here. So it's like we're using a quadrule again. So if I have y prime equals f of ty, if I integrate both sides from tn to tn plus 1, I get y tn plus 1 equals y of tn plus the integral from tn plus 1 f of s y of s ds. So here we have two different ways of approximating its integral. This is the midpoint rule. We evaluate the integrand only at the midpoint of this interval. And then here, trapezoidal rule, the basic trapezoidal rule, non-composite. We evaluate the integrand at the two endpoints and the weights of both will be h over 2. So here we're using the area of a trapezoid to approximate the area of a curve that is this integral. Um, so now both methods are second order accurate, and the reason why um, we we know that is okay. The first non-matched term in the Taylor expansion of the exact solution is order h cubed. So we saw with Euler's method, the first leftover term was order h squared. So that was the first neglected term in the Taylor series. And we got first order accuracy. Now that we actually went ahead and matched from a Taylor expansion of the exact solution, this term that comes from y double prime, which was order h squared in the original Taylor expansion. Note I dropped some terms and divided by h. And the first term we didn't include in Taylor expansion was order h cubed. So that's why we get one extra degree of accuracy by taking this approach. And I could have gone further. I would just need more values of valuations of f, more unknowns to obtain this method. So this is how we derive Runge-Kutta methods using multivariable Taylor expansion of f and matching against the single variable Taylor expansion of y of t. Now, the best known Runge-Kutta method, I won't go over trouble typing it out. Okay, is fourth order Runge-Kutta. I'll make it bigger. So here we evaluate f 4 times, and with these unknowns that are similar to the alpha and beta we had before, but we have more of them, leads to this approach, where the K1, K2, K3, K4 are the stages of a method. So here we have a 4-stage, fourth order method. But as we've already seen, the number of stages is not necessarily the order of accuracy. So we just saw two methods that are second order accurate. One of them had 1 stage and one of them had 2. But generally, more stages does lead to higher degree of a higher order of accuracy. It's just not a uniform thing. Okay. Now, so with a fourth order method, you decrease h by a factor of 10. The error would decrease by a factor of roughly 10,000, as opposed to like Euler's method, it would decrease only by a factor of 10. So the error goes to 0 quite rapidly. Okay. Now, the last thing I want to show you is I mentioned the explicit trapezoidal method. That implies that there's such thing as an implicit trapezoidal method, and that's true. There are actually many implicit methods. So if I evaluate this integral, approximate this integral by evaluating integrand only at tn plus 1, then we have a following. Backward Euler, which is very similar to Euler's method that we saw last time. So hf of tn plus 1, yn plus 1. So the only difference between backward Euler and Euler's method, which is also known as forward Euler to distinguish, or also this is sometimes called implicit Euler and the other is explicit Euler, is that we evaluate f at time n plus 1 rather than time n. So this is the simplest implicit time-stepping method. So because yn plus 1 goes on both sides, we have an equation to solve. Now, if f is a linear function, it's pretty easy to rearrange this and solve for yn plus 1. But if f is a nonlinear function of y, then we have a lot of work to do. So if f is nonlinear in y, must use an iterative method, like Newton's method, something like that. Um, so that seems like a whole lot of work. So implicit methods require more computational effort, more work per time step, but it can often take fewer steps. So the overall amount of work can either balance out or maybe even be less. And this will be especially important for stiff systems of ODEs that we'll come to toward later in the chapter. So any method where you have y n plus 1 on both sides, where you can't just plug and chug to get y n plus 1, that is an example of a implicit method. Okay. Okay, so unlike explicit methods, ones we have seen. So all the methods I've showed you so far are explicit methods. And the informal, but I think informal description, plug and chug, to get yn plus 1. Yn plus 1 only occurs once in the entire description of a method. So you just substitute everything else that you have, like yn, tn, and just work it out, and you get yn plus 1. Now, as far as so another example of okay, so backward Euler like Euler's method or forward Euler, but I'll refer to it from now on, is first order accurate. That's the order h. A second order implicit method is the trapezoidal method. So not to be confused with this explicit trapezoidal method, the implicit trapezoidal method is very similar to this. In fact, I'm going to go ahead and make a copy and then just change it, because the descriptions are almost the same. Okay, so the only difference is instead of approximating yn plus 1 using Euler's method, we just fill in yn plus 1. Okay, so here we have yn plus 1 appearing on both sides of the equation, so we have to use some iterative method to solve for yn plus 1. And when using iterative methods, we already have a good initial guess. So yn is already fairly close to yn plus 1, especially if h is small. Or we can compute this. Like for trapezoidal method, for instance, we have to compute this anyway as part of a method. So we could use it use the Euler's method approximation of yn plus 1 as the initial guess. So I need to make that clear here. So we saw with iterative methods, especially with Newton's, these more rapidly convergent methods can fail if the initial guess is not close to the solution. But the nice thing about time-stepping methods, we already have a natural initial guess. So we don't have to worry about that. And in fact, since there's going to be some error anyway, just from the method itself, we can often get away with just one iteration of Newton's. So a lot of methods actually do that, because the extra computational expense of more iterations could very well not be worth it, just because there's other sources of error to think about that you're not going to be able to overcome no matter how many iterations you perform. Okay. And another thing I want to point out, suppose we have a system of ODEs like this: y prime equals a y. A is n by n matrix. So then we have backward. So I have y n plus 1 is equal to yn plus a, or sorry, ha y n plus 1. Since your function f of ty is just a times y. So this a y n plus 1 is the f part. So now I can rearrange, and I get the following. Identity minus ha y n plus 1 is equal to yn. So now we have an ax equals b problem. So here's your matrix, identity minus ha. Your solution is yn plus 1. Your right-hand side, your b, is just yn. So we have the same system solved many times, different right-hand side. So one of the reasons I gave for justifying the LU decomposition is that we form Gaussian elimination once, we don't do the augmented matrix, and then we save the LU factors, and I've explicitly said, okay, irony, I said explicitly, but I'm talking about implicit method. I stated that this is LU decomposition is convenient for a case where you're solving several systems with the same matrix, different right-hand sides. So you just use the LU factors to work with those different right-hand sides. And this is an example of where that is needed. Because here we are solving the same system, different right-hand sides. So we do LU decomposition of identity minus HA once before any time stepping, and then we use these LU factors to carry out each time step. Okay. Now, in the last few minutes, one thing I want to show back in MATLAB. Okay. Okay. So you have some homework problems where you'll be coding up time-stepping methods. So these will be the outputs, t and y, just like when I use ODE23, MATLAB's built-in ODE solver. And my function is called timestep. So I'll have a function f. Prime equals f of ty, y of 0 equals y naught. And time stepping from 0 to capital T. So I could take as parameters, not the exact same things as in ODE23. We're assuming initial time is 0. So initial value, I'll make sure this is consistent with the homework. Okay. Oh, wait. Oh, actually, no, I did make it consistent with the homework. So T naught up to T final. So T span, initial value, and the difference is I'm specifying step size h. So the initial time is T span of 1, final time is T span 2. So we assume it's a 2-element vector. So we get the initial and final times from the first and second elements respectively. So then, for things to initialize, so t would initially be the initial time. And then, how many time steps? Because we have, so if I use capital N to be the number of time steps, the initial time plus the number of time steps times h should be equal to um, uh, um, the final time, but I'm denoting uh, by TF. Um, okay. Um, Now, so you have a loop that will carry out n time steps, uh, appropriate h. And reason why I say appropriate h is that um, what if final time minus initial time divided by h is not an integer? Then you have to adjust h for the last time step just to make sure you hit the final time exactly. So in the loop, the main step of a method. So what do you do to go from yn to yn plus 1? And the homework problems I have are coding explicit methods, so it's easier to do. So whatever formula describes the method, that's what you put here inside a loop, and then there's things to update. So you update t also, because tn goes to tn plus 1. Storage. So add the new time, new solution to t and y. So before you start, the items from initial condition, the time and a solution value are stored in capital T, capital Y to begin with. And in the loop, you'll keep filling in new values. And that's the procedure. I'll go ahead and post this. Um, so so once your loop is done, that's it. You're finished with your time stepping. Um, so that's the idea here: is that you have initialization, initial storage. Figure out how many steps you're going to take. Use a loop, preferably a for loop, just so you know for sure how many steps you're going to take. Uh, for adaptive time stepping method, you may think differently, but we're not doing that here. Then put in the formula for your method that takes you from yn to yn plus 1, update your t, and then keep your storage up. So make sure you're storing every part of a solution, as I showed you with MATLAB's ODE solver. So then capital T will be a vector of t values, capital Y will be a vector of y values if you have a single ODE. If it's a system of ODEs, then capital Y will be a matrix, and each row is a value of a solution at a given time value. So that's the idea to hopefully get you started with coding some of these methods like comes up in homework. So, all right. Next class I'll get into multi-step methods by contrast with one-step methods.